Everyone, what comes to mind when you think of gold? For most people, things like gold bars and gold rings probably come to mind first. With its unique color, unlike that of most other metals, and a luster that remains unchanged for a very long time, gold has been one of the most special metals in human history, admired across generations and cultures. But why does gold have a yellow color when most other metals don't? And why is it so resistant to corrosion? And among all the precious metals out there, why was gold the one that served as the standard of value for so long? As it turns out, all of these questions trace back to remarkable scientific properties that are unique to gold. In this episode of Dr. Sai Vera Studio, we're going to explore the science hidden behind gold, something most of us take for granted in everyday life. So, let's get started. To start with, how was the element gold created in the first place? In fact, every element on Earth heavier than iron was born in space. Very massive stars release energy through the nuclear fusion of hydrogen, gradually creating heavier and heavier elements. But once they begin producing iron, their evolution effectively comes to an end. In other words, iron is the heaviest element that can be produced through nuclear fusion inside a star. Once a star's core becomes filled with iron, it can no longer support its own immense gravity. Eventually, it undergoes a rapid collapse and explodes as a supernova. During a supernova explosion, an enormous amount of energy is released and vast numbers of neutrons are produced. As these neutrons are captured by atomic nuclei, elements heavier than iron are synthesized. In addition, among the remnants left behind after a supernova are neutron stars, objects with extraordinarily high densities. It is also believed that collisions between these neutron stars can create heavy elements such as gold. The gold produced through these processes was scattered throughout space, and some of it eventually became part of Earth during the formation of our solar system. Even after Earth was formed, countless meteorite impacts continued, and it is estimated that a significant portion of the gold we mine today was delivered to Earth's crust through these impacts. Because gold began its journey in the distant reaches of space before eventually arriving on Earth, its abundance is extremely low. While the exact figures vary from study to study, the average concentration of gold in Earth's crust is generally estimated to be around 0.001 to 0.005 parts per million. To put that into perspective, aluminum and iron make up about 8% and 5% of Earth's crust, respectively. Compared to those elements, gold exists in remarkably small amounts. Given how rare gold is, why has it been regarded as one of humanity's most valuable metals for thousands of years? Let's start with gold's value as a precious metal. When people think of metals, they usually picture a silvery white luster, but gold is special right from the start, beginning with its color. Since ancient times, the color of gold has often been compared to the sun, and across many cultures it came to symbolize eternity, divinity, and uniqueness. So, is gold the only metal with such a distinctive color? In fact, metals that are not silvery white are surprisingly rare. Examples include the reddish color of copper and cesium, which is sometimes described as having a pale gold appearance. However, copper turns greenish blue as it oxidizes, while cesium rapidly oxidizes when exposed to air, making it difficult for either metal to retain its original color for very long. As a result, gold is essentially the only metal that can maintain its characteristic golden color in its natural state over long periods of time. On top of that, gold is chemically very stable. It resists corrosion, reacts very little with its surroundings, and can preserve its beautiful luster for an incredibly long time. It is also unlikely to cause allergic reactions when worn as jewelry. So why does gold have these remarkable properties? The characteristic luster of a metal is determined by the electronic structure of the atoms that make it up. Most metals reflect the majority of visible light, which is why they appear silver or gray. Gold, however, behaves differently. Unlike most metals, it absorbs blue wavelengths within the visible spectrum while reflecting yellow and red wavelengths. As a result, it appears gold in color, somewhere between yellow and orange. And the reason gold absorbs blue light in this unique way ultimately comes down to a fascinating phenomenon known as the relativistic effect. According to Einstein's theory of special relativity, best known for the equation E equals mc squared, an object behaves as if its mass increases as its speed approaches the speed of light. Surprisingly, this concept also applies to tiny atoms. Gold has an atomic number of 79, meaning its nucleus contains 79 protons. Surrounding that nucleus are 79 electrons. Because the nucleus carries a very large positive charge, the electrons closest to it experience an extremely strong electrical attraction and move at incredibly high speeds. Calculations suggest that these inner electrons travel at roughly 50 to 58% of the speed of light. At such speeds, relativistic effects become significant. As a result, the electrons behave as if they have become heavier and are pulled closer to the nucleus, which changes the energy levels of the electron orbitals. This is precisely where gold diverges from most other metals. Because of these relativistic effects, gold absorbs blue wavelengths of light, roughly in the 450 to 500 nanometer range, while reflecting the remaining yellow and red wavelengths. The result is the familiar golden color we all recognize. Gold's remarkable resistance to corrosion is also related to relativistic effects. The electrons inside gold atoms are stabilized by these effects, making them more difficult to remove. In other words, gold is much less likely to lose electrons and become oxidized. Since corrosion fundamentally involves a metal losing electrons, gold remains exceptionally stable because that process does not occur easily. This is why gold reacts very little with most acids and bases and can only be dissolved by special reagents such as aqua regia, a mixture of nitric acid and hydrochloric acid. What's particularly interesting is that relativistic effects are especially pronounced in gold. These effects occur in many heavy elements, but very few exhibit both a distinctive golden color and extraordinary chemical stability the way gold does. That makes gold a truly unique metal, even from the perspective of atomic structure. And perhaps even more remarkably, humanity recognized and took advantage of these special properties long before modern science existed. Yet, gold's enduring value to human civilization cannot be explained by its beautiful color and exceptional stability alone. In fact, there was another crucial factor that allowed gold to become a currency, a precious metal, and a treasured store of wealth. Gold was extremely rare, yet paradoxically not completely rare. Interestingly, gold was actually easier to obtain than you might think. Most metallic elements are more stable when combined with other elements in the form of compounds, which is why they are typically found in nature as minerals. As a result, obtaining pure metal usually requires complex refining processes. Gold, however, is chemically very stable and can exist in its metallic form naturally. Because of this, long before advanced technology existed, people were able to find and use placer gold and naturally occurring gold relatively easily. Historical records suggest that the world's first gold coins were minted during the reign of King Croesus in the Kingdom of Lydia around the 6th century BC in what is now Western Turkey. Gold was not only chemically stable but also easy to work with. It could be melted down and reshaped into new forms, and it could be hammered or drawn into a variety of shapes. On top of that, gold is a dense metal, meaning that a large amount of value can be stored in a relatively small volume, making it convenient to store and transport. These characteristics naturally made gold an ideal material for coins and treasures throughout the ancient world. And gold went even further than that. Over time, it became a metal that served as a standard of wealth itself. In fact, even in the modern era, many countries once adopted the gold standard, a monetary system in which the value of currency was tied to gold. But here we must consider an important question. It's easy to understand how gold's rarity, along with its convenience for storage and transportation, helped make it a measure of value. But was that really enough? As it turns out, there is a major catch when it comes to rarity. What if gold had existed only in a handful of locations on Earth? In that case, gold would have become a resource controlled by a specific country or group, allowing them to manipulate its supply however they wished. And if that happened, the value of money itself could end up being controlled by a particular nation or even a particular individual. But gold is a rather unusual metal. It is extremely rare, yet at the same time it is found in many different parts of the world. No single country can completely monopolize it, but it is also not common enough for its supply to suddenly surge. The reason gold became so widely distributed is that similar geological processes occurred repeatedly across the planet. Over billions of years, magma activity and plate tectonics continually reshaped Earth's interior, gradually concentrating gold within rocks in many different regions. As a result, gold deposits formed in many parts of the world rather than being concentrated in a single region. This gave gold a rather unusual character. It is rare, but not so rare that it can only be found in one place, and it is precisely this unique balance that allowed gold to be recognized as a store of value not only in the past, but even in the modern world. Gold is not just a beautiful metal. Thanks to its unique combination of chemical stability and high electrical conductivity, it continues to play an important role in advanced technologies today. It is widely used not only in highly reliable electronic systems such as semiconductors, servers, data centers, and various military equipment, but also in space technologies that must operate in extremely harsh environments. Let's take just one example, the James Webb Space Telescope, which began full-scale scientific observations in 2022. The James Webb Telescope uses infrared light to observe the early universe and extremely distant celestial objects. Therefore, it requires mirrors that can reflect infrared light very efficiently. Remarkably, gold has exceptionally high reflectivity in the infrared region. On top of that, it is chemically stable, making it an ideal coating material for space telescope mirrors. For this reason, the telescope's 18 primary mirror segments are coated with an extremely thin layer of gold. Gold has been used not only in the mirrors of the James Webb Space Telescope, but also in the Voyager Golden Record, carrying humanity's message as it travels through interstellar space. The gold that humanity valued thousands of years ago is still being used today as a critical material that helps advance some of humanity's most remarkable technologies. Gold has fascinated humanity for thousands of years, and remarkably, the reason lies not in myths or legends but in science. When you think about it, there may be no metal more deserving of the name noble metal than gold. That's all for today's story. I'll be back with another fascinating science story next time. This has been Dr. Sai Vera.